Welcome everyone to the NACOE and WARRIP webinar titled Investigating the Use of Recycled and Reclaimed Plastics in Safe, Sustainable Future Road Infrastructure. We'll begin today by acknowledging the traditional custodians of the lands on which we are meeting and pay our respects to their elders past and present. I extend that respect to any Aboriginal or Torres Strait Islander peoples present here today. Today's webinar is the result of a joint initiative between NACOE and WARRIP. The NACOE program is known as the National Centre of Excellence, is a collaborative research initiative between the Queensland Department of Transport and Main Roads and the Australian Road Research Board, also known as NTRO. And the Western Australian Road Research and Innovation Program, or WARRIP as we know it, is a joint initiative between Main Roads Western Australia and the Australian Road Research Board, or NTRO. Today's webinar has a 1-hour presentation followed by a Q&A opportunity. We welcome your participation, so please submit your questions via the Q&A icon below. And just a reminder, this webinar is being recorded. Our presenters today are Dr. James Grenfell, who's a Principal Professional Leader of the Sustainable Infrastructure Materials Portfolio, and Dr. Chrysoula Pandelidi, Professional within the Materials Testing and Performance Portfolio. I'll now hand over to James.
Thank you, Desiree, and good morning, good evening, good afternoon, wherever you are. Just a quick introduction to this project. As mentioned by Desiree, it's a joint initiative from Queensland Department of Transport and Main Roads Western Australia under the auspices of NACOE and WARRIP. It's to try and increase the awareness of potential uses of recycled plastics in transport infrastructure, construction and maintenance. It has a broader interest nationally. Many of you will know that Austroads has also been looking at the use of recycled plastics in certain applications. The work is to try and create opportunities to use waste materials, but also to focus on the safety of doing so and also some sustainability aspects. And as with all recycled products, it's important that they are safe for the environment, community and workers, do not cause long-term operational issues such as contaminated land, and that they are fully recyclable at the end of their life. They also need to perform at least as well, if not better, than the currently used materials. Next slide, please. So in terms of this particular project, the objectives were to explore ways to safely and sustainably expand the potential use of recycled plastics in transport infrastructure. So it looks at a number of potential applications in addition to asphalt and bitumen, but also touching on that aspect too. It explores the health, safety and environmental impacts of using recycled plastics in road infrastructure, both in standalone applications, but also a particular focus on the use of recycled plastics in asphalt and bitumen. And this work was carried out to complement the investigations that were conducted through the Austroads work. Next slide, please. So what we're presenting today is part of a much larger project. The initial stage 1 was looking at reviewing waste plastics in road infrastructure, where they could be used. It also assessed waste streams in both Western Australia and Queensland and looked a little bit about the recycling and covered a review in terms of desktop from a health, safety and environmental impacts perspective. We're mainly covering the work that's been carried out in stage 2. So we're talking about covering laboratory fuming and emissions, the potential for generation of microplastics and leaching from recycled plastic modified asphalt, and then also the suitability of recycled plastics for use in geosynthetics and also their use in temporary traffic management devices. And this webinar forms part of the knowledge sharing that is associated with stage 2. Next slide, please. And just one note, due to the size and complexity of the plastic streams in Australia and the potential recycled plastics problem in Australia, no single application for using recycled plastics in road infrastructure is going to make a difference on its own. So we need to consider a number of different applications in our research to make any impact on the annual waste plastic stream. So we're not talking about just utilizing it in recycled plastic modified asphalt, but in any number of different applications. And that little schematic shows that each of those different items, so for example, 10,000 bollards could use up 1% of Australia's annual plastic waste stream. And so therefore, even if we considered all 6 of those, that's only going to cover 6% of the annual waste stream. So it's a very complex problem, and multiple applications need to be looked at, but also multiple industries need to be involved to tackle the waste plastic problem as a whole. Next slide, please. So the next thing I'm going to talk about is the potential use of recycled waste plastics in geosynthetics. So first of all, just a quick introduction to geosynthetics. So essentially, I'm talking about things like geotextiles for supporting sprayed seals, geogrids for use in pavement structures or embankment structures, and also geonets that could also be used in geotechnical applications. So I guess the first thing to note is that there's nothing in the specifications to suggest that recycled plastics can't be used in these applications. So as far as we can tell, all of the specifications around these types of products are performance based, and therefore as long as the performance and durability requirements are met, there's no reason why recycled plastic products can't be used. The health, safety and environmental risk profile is not expected to differ from virgin plastic products, and obviously a lot of these products already exist on the market containing virgin plastics and are employed on our road networks. So the typical waste plastic streams that some of these products could target are polyethylene terephthalate PET, polypropylene and high density polyethylene, obviously again dependent on the properties required for the given geosynthetic product. There's some products that already meet current specifications that are available on the market, and therefore that presents us with some potential opportunities for their use in both Western Australia and Queensland. And it's also noted that the relevant plastics, as mentioned above, for the production of these geosynthetics are already being recovered and processed in both WA and Queensland. Next slide, please. So obviously, there are a few barriers at the moment to widespread implementation. I guess the first is production costs. Secondly, making sure that we have a consistent quality of feedstock, and this has been seen as a particular issue in Australia with regards to, I guess, the maturity of the recycled plastics processing industry in Australia. So there are a few geosynthetics on the market in Australia, some of which are utilizing Australian recycled plastic. Some of them are currently made overseas. However, it should be noted that a lot of geosynthetic products, even the virgin ones, tend to be imported from overseas at the moment. I guess in terms of performance, the major concern around recycled plastic products is whether they could meet the long-term creep performance requirements in some applications. Next slide, please. So the next thing I'm going to talk about is the potential use of recycled waste plastics in temporary traffic management devices. Next slide. So again, this provides us with a number of different opportunities for utilizing recycled and waste plastics. And there's a number of different temporary traffic management devices that exist containing containing plastics such as road cones, barriers, bollards and posts, wheel stops, rumble strips, speed humps. And again, there's a number of different plastic types that are currently utilized in the typical virgin products, so PVC, polyvinyl chloride, polypropylene again, low density and high density polyethylene. And I've already covered a number of different applications. Again, the health, safety and environmental risk isn't expected to differ much from that of virgin plastic products. So we're considering products that are standalone plastic products and the virgin equivalents are already used. Again, there's a number of products available on the market that already meet current specifications. So there's an opportunity to engage more broadly across WA and Queensland to encourage their use. And again, it's noted that some of these recycled plastics are already being recovered and processed in both Queensland and WA that could then be utilised directly into these potential temporary traffic management devices. Next slide, please. So again, there's a few barriers that have been identified. I guess one of them is the colouring of recycled plastic materials. It's potentially a little bit more complicated to achieve very bright colours, such as bright oranges in traffic bollards, etc., or traffic cones, I should say. Not impossible, just needs a bit more effort. Again, that can require a good quality of feedstock, and that's just a general comment, I guess, about processing anything with recycled plastics. It seems one of the barriers to utilizing more recycled plastics in temporary traffic management devices is just awareness that there are products that are currently being manufactured out there with certain components of recycled plastics or even very high percentages of recycled plastics. But often people aren't aware that they exist. So it's an opportunity to encourage suppliers and manufacturers to potentially use recycled plastics to give themselves competitive advantage. Obviously, then they can be marketing these products to improve the uptake. And there's opportunities to liaise with industry to help implement resource recycling strategies to try and encourage their production in Australia and also their uptake. Right, now I'm going to hand over to Chrysoula Pandelidi, who's going to talk you through the next step of this presentation. Thanks, Chrysoula.
Thank you, James. As introduced earlier, the incorporation of recycled plastics in bitumen and asphalt may also be of interest. Before we are in a position to recommend their incorporation, however, we need to understand whether they are safe for the operators. To do that, we assessed the fumes and emissions released in a laboratory environment where it was thought concentrations would be greatest. We conducted a comparative analysis between bitumen and asphalt containing recycled plastics and commonly used materials in an enclosed chamber. So that was for binders only. And in the laboratory environment with in-person and static measurements, and that was for both binders and asphalt. Then we were able to evaluate the in-person and static measurements against the Safe Work Australia limits, as well as those recommended by the Australian Institute of Occupational Hygienists. We undertook measurements for volatile organic compounds, polycyclic aromatic hydrocarbons, aldehydes, total suspended particles, and bitumen fumes. So for our investigations, we used a C170 as the base bitumen, and we modified it with some of the commonly used EVA and SBS, and 2 types of recycled plastics. We chose a low-density polyethylene from waste plastic bags, which had been pelletized and was sourced from Western Australia, and a commingled plastic of high-density polyethylene and polypropylene in its as-shredded form, sourced from Queensland. We prepared 4 blends, plus the unmodified C170, which we then used to compact 5 slabs via the wet method, and then we made another 2 slabs, adding the plastics through the dry method. For simplicity in these presentations, we discussed the wet method where additives and modifiers are incorporated during the binder blending process, and that's before mixing with the aggregates, and the dry method where additives are incorporated with the aggregates during asphalt mixing. We do recognize that a third method is discussed when describing the addition of plastics, and that's referred to as the hybrid or mixed method. This method is similar to the dry method, with the difference being that the polymers added are expected to melt or soften during processing. In addition, the added plastics in this research did not replace any of the aggregate portion in the asphalt mix. So in total, we assessed 5 materials during blending and 7 during asphalt mixing. We show here the setup for the measurements in the enclosed chamber, where we used a 5-neck flask containing 500 grams of material, and that was placed in a heating mandrel. The temperature was controlled at 180 degrees, plus minus 10. And according to continuous monitoring, we used the thermocouple that was into the bitumen, which was then continuously also agitated using a low shear mixer. Measurements were taken in accordance with the relevant NIOSH methods, as shown in the graphs on the left. You will also note in this section, as well as those that will follow, that the results are presented in conjunction with each method's limit of reporting, abbreviated as LOR, below which any concentrations present were not quantified. These are notably below any standard exposure limits. So for the volatile organic compounds, the greatest concentration of both aliphatic and aromatic hydrocarbons was measured for commonly used materials. C170 modified with SBS and EVA was found to emit the most aliphatic hydrocarbons, and C170 was found to emit the most aromatic hydrocarbons, albeit marginally when compared to C170 modified with commingled plastics. You can also see here the emission of total volatile organic compounds in increasing order as measured from the enclosed chamber tests. It is evident here that the plastics containing binders emitted the lowest concentration of VOCs, while C170 modified with EVA emitted the greatest concentration of VOCs. C170 and EVA modified C170 were also found to emit the greatest concentration of PAHs, with those measured for C170 being almost double in concentration. We also noted that irrespective of the binder, the PAH most detected was naphthalene. For aldehydes, we detected formaldehydes and acetaldehydes. The greatest concentration of acetaldehydes detected was from the commonly used EVA modified C170, while LDPE modified C170 was found to emit the greatest concentration of formaldehydes. C170 was also found to release the greatest concentration of total suspended particles and bitumen fumes, followed in both cases by the SBS modified binder. So overall, we can see that the emissions from recycled plastics modified C170 at temperatures as high as 180 degrees Celsius were comparable to those of commonly used materials when measured in an enclosed chamber. So the same NIOSH methods were used for the acquisition and analysis of fumes and emissions from binder blending and asphalt mixing activities for the in-person and static measurements. In the photos to the right here, you can see the position of the samplers, but in the case of asphalt mixing, the static sampler was moved near the operator's working space around the laboratory. In some cases, the VOCs measured by the incorporation of recycled plastics were greater than those of the conventional materials. These were primarily measured during the asphalt mixing activities. For example, we can see that the wet mix using the binder modified with HDPE and polypropylene emitted the greatest concentration of aromatic and aliphatic hydrocarbons as measured by both the static and the in-person samplers, when compared to the asphalt mixing, which was using conventional materials. Importantly, though, all the total VOCs measurements were significantly below the time-weighted average as recommended by Safe Work Australia. In the worst-case scenario of VOCs emitted during the wet asphalt mixing of HDPE, the containing binder, the total VOCs were at 0.1% of the Safe Work Australia limit. In the case of aldehydes, the incorporation of recycled plastics was not found to result in the emission of naphthalene or other PAHs at concentrations greater than those emitted by the commonly used materials. Naphthalene is the only PAH for which Safe Work Australia has set an upper exposure limit. The naphthalene emission of EVA modified binder, which was the one found to emit the greatest amount according to the static sampler, was found to be 0.08% of the set limit by Safe Work Australia. In some cases, the emission of aldehydes, specifically formaldehydes and acetaldehydes, from the samples containing recycled plastics exceeded those of conventional materials. In all cases, however, those were found to be below the limit set by Safe Work Australia. The greatest concentration of formaldehydes was emitted by the EVA modified binder as measured by the static sampler, which was approximately 1.3% of the allowed limits, and for the acetaldehydes emitted by LDPE modified binder, which was at 0.03% of the allowable limits. All bitumen fumes were below the detection limit of 0.05 milligrams per filter. The incorporation of recycled plastics was found to result in the increased release of total suspended particles in some cases. Safe Work Australia has not set an upper limit for the total suspended particles. However, the Australian Institute of Occupational Hygienists recommends that workers are not exposed to more than 5 milligrams per cubic meter in a working day. For the graph to the right, it is evident that even at their highest concentration detected by the in-person sampler during the dry asphalt mixing of HDPE polypropylene, the measured emission was 19% of that limit. So following these trial methods, we were able to put forward an assessment protocol, which would allow for an initial benchmarking activity using the enclosed chamber method, and a method for the assessment of fumes and emissions in a laboratory environment as experienced by the operators and others potentially working near these workstations, which can be assessed against Safe Work Australia limits. As a first step, baseline material and binders containing recycled plastics can be comparatively assessed in an enclosed chamber. The temperature of 180 plus minus 10 degrees, which is typical for blending polymers in the laboratory, is recommended here, even for the base bitumen, just for a better comparative analysis. We found that all target fumes and emissions could be assessed this way, although we do recognize limitations relating to oxygen flow and availability within the chamber. Following the initial comparative assessment, a more comprehensive assessment of fumes and emissions as emitted in the laboratory environment can be then undertaken, specifically in cases where the results from the step 1 assessment for newly introduced materials exceed those of baseline materials. As we discussed earlier, the enclosed chamber results are not representative of the operator's exposure to fumes and emissions. Therefore, in cases where they are found to be greater than the benchmark materials, their assessment using static and in-person samplers could provide results that can then be compared to Safe Work Australia limits, ultimately deeming them safe for use or not. In addition to worker safety, the impacts to the environment were also needed to be assessed. In this research, we considered the potential release of leachates and microplastics. Therefore, in this section, we include the methods we used for the assessment of leachates and microplastics, where we tried 3 different methods to measure leachates, one assessing the binders before mixing with aggregates, and a couple using a loose asphalt mix, the loose asphalt mix. One where we crushed the coated aggregates to size, and another where we selected only the appropriate sized aggregates without crushing them. As far as microplastics were concerned, we considered methods for both their qualification and their quantification. To prepare the binders, we used a high shear mixer at 4,000 RPM. The binders were kept at 180 plus minus 10 degrees Celsius for 1 hour under a blanket of carbon dioxide, and that was to prevent oxidation. We then used these binders to prepare 4 slabs. Another slab was made using unmodified C170, and 2 more via the dry method incorporating the recycled plastics, as I mentioned earlier. For worst case scenario, we also subjected the prepared slabs to thermo-oxidative aging following AASHTO R30 method. To assess the potential release of leachates, we tried a couple of different things, as said. Firstly, we tried to assess leachates from the binder in a method similar to what was described by Greg White. We submerged the binders in deionized water and covered with aluminium foil, and then agitated using a magnetic stirring at the ambient temperature. Then we placed them in the oven at 40 degrees Celsius for 18 hours, and then repeated that agitation process for another hour. Once we finished with the exposure, we filtered the potentially contaminated deionized water through a 4 micrometer mesh filter. The water was then cold evaporated under nitrogen, and the residue was submerged in 5 milliliters of ethanol and prepared for GCMS. We were interested to see whether any peaks for PAHs, bisphenol A, phthalates, styrene, and hydrocarbons could be detected during this process. But as you may be able to see in the results to the right, we did not identify any peaks different to those of ethanol in any of the samples. We also tried to assess the loose mix asphalt for leachates using the Australian standard leach procedure. This method is commonly used to measure leachates in soil. We tried this method by both crushing our loose asphalt mix to size, where I will refer to this as a crushed, and by sieving the loose asphalt mix to include only those of acceptable size, avoiding crushing. I will refer to those as uncrushed. We then assessed for metals, phthalate esters, VOCs, PAHs, phenolics, and other polar compounds. Before I present the results here, I do need to say that I will talk a lot about groundwater investigation level, abbreviated here as a GIL in this presentation. According to the National Environmental Protection Measure, this is the level above which further investigations are required before they are deemed safe for the environment. Now, looking at the results for PAH leachates from a crushed loose asphalt mix, only those of C170 and EVA modified C170 were above the limit of reporting, and all were below the groundwater investigation level. The results from the uncrushed loose asphalt mix were the same as those of the crushed sample as far as the PAHs were concerned. For the crushed samples, water leachable metals, namely aluminium, nickel, and zinc, were all detected. Zinc and aluminium were all at or above the groundwater investigation level for fresh water. These metals have previously been associated with quarrying activities, and so we suspect they were detected due to the presence of aggregates in the sample. Also, C170, EVA modified C170, and plastics modified samples via the dry method were also found to release nickel at concentrations above the fresh water and marine water groundwater investigation level and at the drinking water limits. EVA modified C170 and LDPE modified C170 via the wet method were also above the groundwater investigation level for zinc. The results changed when uncrushed loose mix asphalt was assessed. In this case, zinc was not detected above the limit of reporting for any of the samples. Aluminium was still present in all samples and in all cases above the groundwater investigation level. Nickel was also still detected by C170 and EVA modified C170, in both cases above the groundwater investigation level for marine waters. We understand that nickel can be present in bitumen sometimes. Since we were able to detect leachates such as aluminium, which is not expected to be present in the bitumen or any of the additives, both in the crushed and uncrushed loose mix asphalt, we cannot confidently express that the method can exclude the effects of aggregates. Therefore, we conclude here that a method for investigating the binders before they're mixed with the aggregates is potentially more suitable. We note, of course, that the method described here did not bring forward any relevant readings. Now, this could either be because no leachates were present in the samples or because the method was not calibrated to the analytes of interest. We feel that this method still warrants further investigations. Now, to understand the potential release of microplastics by the manufactured and aged asphalt slabs, we use the custom-developed abrasion device to abrade the surface for 1 hour. The slabs were sprayed with water to prevent overheating due to friction and also capture the released dust. After abrasion, the slabs were rinsed with water to wash off all captured particulate matter, and the contaminated water was collected in trays, and you can see those trays here to the right. The water was then evaporated in a dehydrating oven at 50 degrees Celsius, and the particulate matter was collected. As only particles smaller than 5 millimeters can be classified as microplastics, the particulate matter was sieved and only particles for smaller size were used for this analysis. To quantify the microplastics in the particulate matter, we used thermogravimetric analysis. This method analyzes between 5 to 10 milligrams of the sample of interest. The specimens are heated at the selected rate under an atmosphere of choice. Here we used a heating rate of 5 degrees Celsius per minute for high resolution measurements, and that was at the region of interest, which was between 250 and 550 degrees Celsius, and an inert atmosphere. As the samples are heated, the bitumen and plastics degrade, leading to mass loss. So in the image to the right, you can see an example of the mass loss and derivative curves generated by this method. As the aggregates are not expected to degrade within the temperature range used in this analysis, all mass loss above 200 degrees Celsius was attributed to the degradation of bitumen and plastics. Also, we used the Victorian mix, which included hydrated lime. Hydrated lime does not degrade within the examined range. As you can see it does degrade within the examined range, and you can see that on the orange curve in figure A. However, we did not find any peaks that coincided with that of hydrated lime. The figures in the slide show the results for HDPE modified asphalt by the wet method. But this analysis was undertaken for all particulate matter from all 7 slabs, as well as for the C170 and all 4 binders and all 4 additives. So for this analysis, we assume that the binders used do not segregate, as this is the requirement for national and state specifications. Therefore, even though the degradation regions of the C170 and additives overlapped, we could calculate the concentrations of plastics based on their concentration in the blend. So for the dry blend of HDPE and polypropylene, which did not soften during the mixing process, we were able to measure the concentration of plastics directly, as you can see in the figures to the right here. So overall, most of the abraded matter was found to comprise by aggregates, followed by bitumen. The concentration of microplastic was found to be dependent on their concentration in the blend, and so the concentration of microplastics from blends modified with LDPE and HDPE polypropylene were found to release more microplastics. However, we need to note that their concentration in the blend was 10%, which was greater than that of the SPS and EVA in the respective blends. So the way in which microplastics affect the environment have not yet been conclusively defined. Therefore, even though their quantification was important, it was thought that finding methods for the qualification was also necessary. In this method, we took the dried abraded matter, dissolved the bitumen using low-odor kerosene, using magnetic stirring, and filtering the solution until clear. Then we used glycerin to separate the aggregates from the microplastics via density separation. Finally, the floating microplastics were collected using a pipette. The microplastics from this method could then be analyzed for morphology using optical methods, and polymer type using spectroscopic methods. We found that the method could successfully dissolve bitumen for most samples. SPS modified plastics were an exemption due to the similarity of its solubility parameters with bitumen. For SPS, a different solvent or combination of solvents could address this challenge. However, we wanted to assess the method using solvents that are readily available in a bitumen laboratory. And that was just for this exercise here. We could also successfully collect microplastics from the solution following the density separation, which then could be analyzed under an optical microscope, for example. Using this method, however, we were also collecting fines that remain floating on the surface, possibly due to surface tension. So when looking under the microscope, we need to be careful that what is analyzed is indeed microplastics. Using methods such as polarized lenses or UV light, among others, could help with this. In addition, we need to note that the floating microplastics were invisible to the naked eye, so collection needed to be confirmed throughout. So following this assessment for microplastics, we were then in a position to recommend a protocol for their assessment. This protocol involves avenues for both their qualification and quantification. Now, as limits for microplastics have not yet been set, it is recommended that the release of microplastics from recycled plastic modified asphalt is compared against commonly used materials. It is also proposed that the slabs are assessed after simulated aging, either thermooxidative or UV or both. The abrasion duration can be tailored to the amount of material required. However, we found a minimum of 1 hour to be suitable to remove a sufficient amount of material, and that was also creating a surface that was similar to that of an aged road. For the quantification of microplastics, thermogravimetric analysis was found appropriate. Due to the small amount of material analyzed per specimen by this method, a minimum of 3 specimens should be considered per sample group, and their average should be reported. Bitumen dissolution and density separation can then be used to the remaining of the abraded matter in order to assess the morphology of the released microplastics and find the type of plastics present. So now I will be passing on back to James. Thank you.
All right, thank you, Chrysoula. So now I'm just going to cover a bit about the expected performance of recycled plastic modified asphalt. So a little bit of an introduction. First of all, it's important to say that this work was a desktop comparison between published results available around recycled plastic modified asphalt, where possible, undertaken using Australian Road Authority test methods. And it was to try to give us an idea of where Australian state road authorities could potentially utilize recycled plastic modified asphalt. So I guess the focus is understanding where they, or what mixes they're presently using, for example, in terms of wearing courses on highways and freeways, or what they're doing in terms of asphalt base courses. So just to put, I guess, Western Australia and Queensland into context, typically in their asphalt wearing courses, they would be using SBS modified asphalts in dense graded asphalt and in stone mastic asphalt and open graded asphalt mixes. And I guess one of the main reasons for this, especially for the dense graded and the stone mastic asphalt, is to get improved fatigue cracking performance. So when I say SBS modified asphalts, I'm considering A10E, A15E type binders. There's some use of crumb rubber in both open graded asphalt and also gap graded asphalt in both Western Australia and Queensland. And there's still some use of unmodified C320 binder in asphalt in lower trafficked applications. One other thing to note is that in certain hot locations that are of considerable risk of permanent deformation, and in particular in WA, that EVA modified asphalt is sometimes used in dense graded asphalt. So in terms of Australian context, EVA would be A35P binders. Typically in both states, the asphalt base and binder courses that would be used would either be using unmodified C320 or C600 binder in dense graded asphalt, or potentially utilizing high modulus base asphalt or high modulus asphalt such as EME2, so enrobe module 11 2. Next slide, please, Chrysoula. So what we're trying to do here is utilize available published data on recycled plastic modified asphalt and compare that with both unmodified asphalt and SBS and EVA modified asphalt. So trying to compare the typical performance of recycled plastic asphalt with the typical asphalts that are used in different parts of the pavement structure in both Queensland and WA. So the focus was looking at, obviously, the data available on recycled plastic modified asphalt mixes, but also comparing that with published data on unmodified binder mixes, so C170, C320 binders, or even C600 binders in asphalt. SBS modified binders, so the A10Es, A15Es, and EVA modified binders in asphalt, such as A35P. And the focus of this comparison was on flexural stiffness, fatigue cracking, and also permanent deformation of the resultant asphalt mixtures. Next slide, please, Chrysoula. So the first area of interest was flexural stiffness, and in Australia, typically we would test according to AGPT T274. So I guess one thing is it was quite difficult to do exact comparisons just due to small data sets or slightly different parameters being used in each of the different research. But generally, the recycled plastic mixes were similar or a bit stiffer than unmodified asphalt mixes, unmodified bitumen asphalt mixes, and similar to the stiffness of the SBS type modified mixes, not quite as stiff as the EVA modified asphalt mixes, but again noted that there's very limited use of that type of asphalt in Australia. So I guess one of the reasons why there's such a small data set to be compared is that there's a lot of different parameters that could be looked at, many different manufacturing methods and binder sources, and also potentially differences in whether it was laboratory produced mix or field manufactured mix. Obviously, I guess another thing to consider is even the binder's storage stability in terms of making unmodified, polymer modified or recycled plastic modified binders for use in recycled plastic modified asphalt. Next slide, please. Fatigue cracking is obviously of particular interest and probably, I guess, the major concern when designing a pavement. So in this particular part of the study, we were considering flexural fatigue data as per Austroads AGPT T274. And the findings were generally that the wet mix recycled plastic modified binder manufactured asphalts had similar fatigue results to unmodified C170 binders or C320 binders, but were not as resistant to flexural fatigue as some of the high performing polymer modified binder asphalts, so the A10E and the A15E. Recycled plastic modified asphalt produced through the dry method again presented similar test results to unmodified C320 hot mix asphalt, as might well be expected, given that the recycled plastic incorporated through this method isn't expected to modify the binder properties. There was a suggestion in the data that potentially the recycled plastic modified asphalt might have a higher temperature susceptibility compared to some of the premium polymer modified binder asphalts. Next slide, please. So the last area of interest was permanent deformation properties. This work looked at tests undertaken either through AASHTO T324, which we would call Hamburg wheel tracking, or AGPT T231, which is typically undertaken in Australia using what we call a Cooper's wheel tracker or small scale wheel tracking device. So given that a lot of the existing research carried out considering Australian test methods were undertaken either in Hamburg wheel tracking or the small scale wheel tracking, it was difficult to make direct comparisons just due to the differences in test methods. But as unmodified bitumen asphalts were utilized in both sets of testing results, we can make some inferences about the expected relative performance comparing recycled plastics to some of the premium polymer modified binders. And so I guess the first thing to note is that the recycled plastic modified blends, both wet and dry mix, have similar rutting resistance to unmodified C320 modified asphalt, but not as good as some of the premium polymer modified binders. And the best performing, as you might expect, was the EVA modified asphalt. So the asphalt produced with A35P binder. Next slide, please. So I'm just going to run through a few key messages from the performance testing investigation. First thing to note is that there is still limited available data sets or limited available published data sets to allow us to draw firm conclusions. But generally, the recycled plastic modified asphalt appears to have similar properties to typical unmodified asphalts, for example, the C320 binder-made asphalt, but not quite as good, or not as good as the high-performing premium polymer modified mixes, especially in fatigue performance. So recycled plastic modified asphalt is generally a bit stiffer than unmodified bitumen made asphalt, and the rutting resistance is marginally better. But again, it's not as good as the premium polymer modified asphalt in terms of its rutting resistance, and definitely not as good as A35P modified asphalt or the EVA modified asphalts. Again, recycled plastic modified asphalt seems to have similar properties to unmodified asphalt in fatigue, potentially slightly better in some cases, although there was that question mark about slightly higher temperature susceptibility. However, it doesn't perform as well in fatigue as the A10E and A15E modified asphalt mixes. So I guess the main conclusion from that is that the main application for the use of recycled plastic modified asphalt would be where a unmodified bitumen asphalt is currently used, where we can be confident that the recycled plastic modified asphalt would have similar, if not fractionally better, performance than the unmodified asphalt. Right, next slide. So now just running through a few conclusions and recommendations from this work. So I guess the first thing to note is that obviously there's a lot of potential applications for the use of recycled plastic, and I think I've scanned through some of the questions already. There's a number of other applications that we are obviously not considering in this research. One of the reasons for that was because it was felt that that research was already being undertaken in other projects, and therefore we didn't need to investigate that too much in this particular project. And so our focus was mainly on areas that hadn't really had a lot of research into their use. So hence the focus on the use of recycled plastics in geosynthetics. So there are opportunities to use recycled plastics in geosynthetics. So that could be within geogrids, geotextiles, geonets. There's some opportunities to use recycled plastic in traffic management and temporary traffic management devices, such as cones, bollards, wheel stops, speed bumps, safety barriers, rumble bars. Most of the limitations are around the recycling industry in Australia, which is still in development, and allowing us availability to enough recycled plastic or recycled processed plastic of the required quality to produce these various different products. Recycled plastic can also be used in asphalt and can be incorporated through either a wet or a dry process, or kind of a mixed process or a hybrid process where we're adding in lower melt polymers directly into the asphalt plant with a view to blending with the bitumen. Generally, the recycled plastic asphalts that we make from recycled plastics is unlikely to have the same performance as a typical polymer modified asphalt, but can give performance that is similar or slightly better to unmodified bitumen manufactured asphalt. Therefore, recycled plastic modified asphalt is more applicable for use on local or local government roads or low trafficked applications, and applications where unmodified binders are currently used in the asphalt for those locations. Next slide, please. So then we focused our attentions to laboratory testing on the health, safety, and environmental performance of recycled plastic modified asphalt. And as you heard before, some proposed assessment protocols have been developed. So some of those were in fuming and emissions, and for recycled plastic modified asphalt, the fuming and emissions were found to be comparable with conventional asphalt or polymer modified asphalts that are already currently being widely used. It's recommended that further research be undertaken on leachability, and I guess a lot of that is around the fact that there aren't any suitable test methods to understand the potential for leachability of plastics from bound asphalt applications. Most of the leachability tests are more suited to unbound granular materials. So further research might be required here just to check that there aren't any concerns. However, the potential for the generation of microplastics from recycled plastic modified asphalt was again found to be comparable to that from either unmodified asphalt or polymer modified asphalts that are again currently widely used and accepted on our road network. I think that now brings us on to questions. So I think I'm handing back to Desiree to manage this part of the session.
Yes, James, I think one of the first questions that I might just pose is if you could just clarify a little bit more about the wet and dry two processes and what exactly you were referring to there.
Yeah, thank you, Desiree. So essentially, there's kind of three different methodologies for incorporating recycled plastics into asphalt. The first one, and probably the one that's likely to give the best outcome, is through what we would call a wet process. So we're taking lower melt temperature recycled plastics such as low density polyethylene, linear low density, potentially high density polyethylene, and blending that in directly with the bitumen to create a waste plastic modified binder that we then use to make our asphalt in a similar way to a polymer modified binder. So adding in the resultant recycled plastic modified binder now into the asphalt plant to make a recycled plastic modified asphalt. The second method is what we would term as a dry method. So that would be taking some of the higher melt temperature polymers such as PET or ABS. They would be processed or shredded down to a fairly fine size and can be used as a partial fine aggregate replacement. So again, or in this case, adding in with the fine aggregate component into an asphalt plant. Due to their melt temperatures, they're not expected to change during the asphalt plant manufacture and sit as a partial fine aggregate replacement within the asphalt mix. The final method, the mixed or hybrid method, is where we're taking some of the lower melt temperature recycled plastics and adding those in again at the asphalt plant, but with a view that they will combine and blend with the bitumen as it's added during the asphalt mixing process, with a view to modifying the bitumen and producing a recycled plastic modified asphalt that way. And I guess one of the reasons for trying to add the recycled plastics that way is to overcome some of the issues that are seen with incorporating recycled plastics through the wet process directly into the binder. Recycled plastics don't have good storage stability in bitumen and therefore tend to separate out quite readily or quickly. And so to overcome that issue, there's the opportunity to potentially add the recycled plastics in at the asphalt plant with a view that they can partially blend with the bitumen, but also to overcome any issues of storage stability and therefore create a much more storage stable or homogeneous resultant mix.
Another question, just following on from some of that, is just to find out, is there any opportunity for recycled plastic in sprayed sealing?
Yeah, that's a good question, and I think it has been investigated to a certain extent in industry. Again, the problem is lying around the fact that it's difficult to blend recycled plastics into bitumen, especially to create a storage stable blend, and therefore, given some of the distances involved with transportation of binders for sprayed sealing, that becomes an issue. One of the other issues is around I guess the consistency of the resultant binder and being able to pass that through the sprayer bar of the asphalt, as the binder spreader. So if the recycled plastic isn't fully blended or well blended in the bitumen, due to its consistency, it can potentially block some of the spray nozzles in the spray bar, which isn't desirable, and therefore I think people have moved away until better processes can be created to achieve either more storage stable binders or much more homogeneous smooth binders, that the risks are too high at the moment in terms of operational and construction risks to utilize recycled plastics in sprayed seal applications.
Another question following on from the laboratory testing that we've done and the emissions and fumings, there seem to be a few concerns around and just clarifications needed in terms of the real life application versus the laboratory testing of the fuming emissions. How do we think that will translate?
Yeah, so I guess one thing to note is that the work that was undertaken here was essentially carried out as a benchmarking process to assess the generation of fuming and emissions of the recycled plastic modified bitumens and asphalts in comparison to unmodified asphalt and premium polymer modified asphalt in the laboratory. Part of that, again, was to allow us to undertake this testing under very controlled conditions, but it did obviously allow us to look at some kind of worst case scenarios in terms of very enclosed spaces in which the emissions were monitored in. And therefore, given the fact that the results showed that there was no concern or no greater concern in the emissions from the recycled plastic modified bitumens and asphalts compared to the unmodified binders and polymer modified binders that are currently being used, that those findings would scale up to the field. So there was nothing of concern that was found in the recycled plastic modified bitumens and asphalts. I guess potentially a slightly unpleasant smell, but not a health hazard for humans. And therefore it would generally be expected that in the field, in much more open conditions and where there's more airflow, that the risks would again be essentially lower. Having said that, it is obviously important to wear appropriate PPE when constructing in the field anyway, and following safe working methods to make sure that no workers are overexposed to fumes from the back of asphalt pavers or during the compaction processes.
Regards the Austroads works, just understanding how our research relates to that work would be great as well.
Yeah, so obviously we understand that there's a lot of work that's been undertaken in the Austroads space, especially in terms of recycled plastic modified asphalt. The work that was carried out at RMIT through Austroads was very much focused on recycled plastic modification of asphalt and understanding how that could be carried out. This work is a bit broader in the sense that it's looking at many other applications for recycled plastic in transport infrastructure in general, but also obviously it had the focus on desktop study of performance of asphalt, just to understand where it could be applicable to both WA and Queensland from a desktop study perspective, but also undertaken to be complementary to the Austroads work in terms of fuming and emissions and also microplastics generation. So obviously due to the sensitivity or concerns over health and safety and also what that might mean to the environment, one of the major questions that both TMR and Main Roads had were, if you propose the same question to an alternative set of researchers and they developed their own methodologies, would they come back and provide essentially the same answer as the Austroads work? And I think we can generally say that the findings from this particular work are in agreement with the Austroads work, and therefore confirm that there's no major concerns over fuming emissions or potential microplastics generation from recycled plastic modified asphalt.
Next question that's quite popular seems to be just about the more in detail research and publishing and when to expect that.
Yes, that's a good question. So some of the reports associated with this project will be published through the NACOE and the WARRIP websites in due course. Some of the work is currently for internal use only. So I guess there'll be question marks about whether everything will end up in the public domain from this particular project. And obviously one of the other things is, as we work more and more in this space, I mean, in general in Australia, there's going to be more and more available data on the performance of recycled plastic modified asphalt in an Australian setting. As most people in the webinar will know, the Austroads work has been published that very much focuses on recycled plastic modification of asphalt. And so again, there's a number of reports that are available and free to download through the Austroads website, and also webinars that are free to watch there. And as mentioned, there's a number of other pieces of work that are also investigating some of the other applications of recycled plastic. And again, some of that work can either be found through, say, Austroads. So my understanding is that there's some work currently being undertaken looking at flexible plastic pipes, whether or not that's expanding to the incorporation of recycled plastics into that, I'm not sure. There is a specification available through the Austroads website for plastic noise walls, which is a performance-based spec and therefore allows recycled plastics to be used as long as performance requirements can be met. And again, there's other projects that are being undertaken through either NACOE or WARRIP that incorporate or look at the use of recycled plastics in other applications that can potentially be found on those websites and free to download.
Are we aware of any field applications that have used some of the recycled plastics?
As in specific case studies in asphalt or the other applications? I think everything that I've shown today, we have seen examples of where recycled plastics have been utilized in geosynthetics in Australia. I'm not sure of any specific locations, but it's definitely been done. I think potentially the geotextiles is potentially the most prevalent for supporting sprayed seals, and I know of some trials utilizing a product containing some recycled plastic content that's definitely been carried out in Victoria. Not sure for the other states. And again, there's one manufacturer that can produce, I think, a pretty much 100% recycled plastic geogrid for, I guess, structural applications. As far as I know at the moment, that product is manufactured overseas and imported, but the equivalent virgin products are also manufactured overseas. I couldn't tell you where there's any specific field trials in that case. Again, in terms of the temporary traffic management devices, all of the solutions that were discussed there are recycled plastic containing products available on the market in Australia that meet the specifications in both WA and Queensland. Some potentially can be manufactured or are being manufactured at the moment in Australia. I know that there's also several that are manufactured overseas and imported. I couldn't tell you where there's specific cases that they have been used. So potentially there could be information from product suppliers in terms of case studies on where they've been used in an Australian setting. There's been a number of trials around the country, I guess, by various contractors of recycled plastic modified asphalt. And so most of the major contractors have their own proprietary mixes or blends that have been utilized in Australia. And again, as far as I know, there's a larger field trial in preparation through Austroads to look at recycled plastic modified asphalt in a asphalt wearing course setting.
In regards to our testing, we were talking about the sampling of the VOCs and the PAHs. Just checking, were the flow rates the same? And if not, how did we make sure that that wasn't impacting our results?
The flow rates in what sense, in terms of?
The sampling of the VOCs and PAH. I think there was. Is that a Chrysoula question?
Yeah, I think I'll hand that one to Chrysoula.
So yeah, so we used pumps to control the flow rates, and we made sure that the pumps weren't obstructed in any way, and the flow rates were determined according to the specified methods we used for testing.
And they were the same?
As per the method. Okay,
yeah. And then the other question that might be yours, Chrysoula, was just understanding the NIOSH standards and the Australian thresholds, and how we applied and measured against those.
Yeah, so the thresholds from the that were set based on the Safe Work Australia, they just give us the outcome, the measurement. So they say that if a worker shouldn't be exposed to more than this much. The NIOSH method is what is used to do the sampling during the process, and they were conducted using a NATA accredited subcontractor for these test methods, and who practices in Australia, of course. Yeah.
Yeah. So the NIOSH test methods are essentially widely accepted internationally, but there's local guidelines in terms of exposure limits. So the results from the tests were then compared against the allowable levels in Australia safe work literature.
And then we were just, some of the results, is there any insight into why we think the dry mix blend contained the highest amount of microplastics?
So this was when compared to the wet blends, and that was purely based on their concentration in the blend. So the blends that we did with recycled plastics, they were made at 10% recycled plastics, while when we used the EVA and SBS blends, we made compliant blends based on the Austroads ATS 3110. So these blends didn't require as high concentrations for the additive. So as a result, like with the calculations, that's how that came up to be higher, comparatively higher, but only depended on their concentration in the binder.
Yeah, so essentially that dry method was almost a absolute worst case scenario and unrealistic for the amount of recycled plastic that would be incorporated in real life through that method. It was also an opportunity then to actually really test how good the method was that we developed for picking up microplastics as well.
Just trying to figure out if there's any other additional questions. There's so many in the chat. So thank you everyone for participating so well with the Q&A. There is a question just about our definition, how we defined recycled plastics use in pavement, and whether or not we are including the plastics used in roads previously, such as the geosynthetics.
Yeah, I guess in terms of the plastics that we've been looking at, in terms of the geosynthetics and also the temporary traffic management devices, the work looked at processing in Australia of plastics or recycled plastics of a similar nature to the what the virgin products were made from, just to get an understanding of the recycling industry's capacity to recycle and process those different plastics, with a view to understanding whether there was the opportunity to develop, I guess, a manufacturing industry around recycled plastics in Australia for some of those different applications. In terms of the asphalt testing, essentially, again, we looked at available recycled plastic or processed plastics from both WA and Queensland, and selected some that were the most prevalent and the most relatable to some of the recycled plastics that were tested in the Austroads work. So the Austroads work undertook, I guess, some initial testing on a very wide range of recycled plastics, and then took some of the ones that looked most promising forward into asphalt mix testing. So I think they started off undertaking work very much looking at compatibility and understanding how easy it was to blend different waste plastics in with the binders, and then selected the best ones for further work in terms of mixture testing, and obviously looked at some in terms of their melting temperatures as to which would be most appropriate for incorporation through a dry method. Most of our work focused on what opportunities there were in the wet method, because that was seen as a way to potentially improve the properties of the asphalt, whereas the dry method was considered to at best give equivalent performance, and potentially, as you're replacing some of the fine aggregate with a recycled plastic that might not be as stiff, that potentially it could actually create a product that would be less good in performance. So our focus wasn't on the dry process. So essentially, again, we selected some recycled plastic sources in both Queensland and WA that had parallels with some of the sources that were undertaken in the Austroads work for comparison. But the plastics that we sourced were very specifically sourced from Queensland and WA and had been processed there. Whereas I think a lot of the infrastructure for recycling in the plastics industry in Australia generally is probably more focused around Victoria and New South Wales. So potentially the recycled plastics utilised in the Austroads research generally came from either Victorian or maybe New South Wales sources.
One more question about the lifespan that we expect from these. Is there any, do we have any ideas? Has there been any testing that helped us understand how long these mixes might last once applied?
And I guess the complication here is obviously to have absolute confidence in long-term performance, we need long-term field trials. So at the moment, most of the inferences are made around laboratory fatigue testing, which essentially the fatigue life is likely to be the deciding factor on the long-term or the longevity of these recycled plastic modified asphalts. And therefore, at the moment, I think we can only really say that we would expect the recycled plastic modified asphalt to have a similar or potentially slightly longer fatigue life than an unmodified asphalt made with, say, a C320 binder. I know that obviously there's been a number of field trials around Australia, maybe in the last 5+ years now. So there's obviously more data being generated in terms of field performance. I'm not sure how many of these field trials were monitored independently and also had control sections laid next to them for comparison. I guess that's probably the next step where the Ostro's work is going, is to actually have a much more controlled field trial, inviting a number of different recycled plastic modified asphalt mixes to provide materials for one very large field trial site and undertake ongoing long-term monitoring against controlled materials with known performance, which obviously is then going to give us a much more comprehensive picture as to how these types of mixes are likely to perform into the future, and I guess give us a better understanding of their design lives or longevity.
I think we probably have time just for one more question. Maybe just considering the quality and how to maintain the quality of our source plastics, obviously knowing that that would have an impact on any application that we use it for.
Yes, I guess one of the things is obviously, ideally we want to try and tackle what we would consider to be the problem plastics, the ones that can't be easily recycled to a level at which they can be recycled back into products of a higher value. And therefore, I guess that then suggests maybe there's an opportunity to utilize some of these plastics in transport infrastructure applications, especially in terms of modifying asphalt. I think at the moment, obviously, all the work is suggesting that a certain amount of processing is still needed on those recycled plastics to ensure consistent feedstocks to allow resultant properties to be controlled to a level that we would be comfortable in allowing them in a road setting. And obviously we need to make sure that the properties of the resultant recycled modified asphalt is at least equivalent, if not better, than traditionally used materials such as the unmodified bitumen asphalts. And therefore, potentially that also then obviously adds on to the costs. So I think there's still work to be done by the recycling industry to increase recycling rates, to bring costs of recycled products down, and also be able to make processes that always are producing very consistent recycled plastic feedstocks with consistent properties that can then potentially be used in various applications, be that standalone products or potentially as a potential additive to asphalt.
Thank you, James. And thank you to Chrysoula and James both for their presentations today. And thank you to everyone that has dialed in and joined us. We will definitely be putting things up on the WARRIP and NACOE websites, so feel free to keep an eye out for our publications. Thanks, everyone.
Thank you.